Good morning, everyone. So last class we were discussing a method of dimensionality reduction called the principal component analysis. So where you have vector x of dimension n, and we reduce it by linear transformation by multiplying by weight matrix W, and we reduce it to a vector of dimension vector y of dimension m, where m is less than n. Then from this y we reconstruct x, which we call x hat, in such a way that x hat is as close as possible to x. So obviously, since we are losing some information in transforming from x to y, right, you may not be able to perfectly reconstruct x unless y has a data x has a very special structure where certain dimensions are completely irrelevant, or there's no information. Right, there will be some loss. Only thing is now, how do you minimize that loss? How do you produce this y so that this loss or error between x hat and x is minimized? So we said, the kind of pattern that you will see here, that you're likely to see, is that if m is equal to n, obviously the error will be 0. You can always, it's trivial. And as you reduce m from n, what you will see is the error will keep climbing up, and when m equal to 1, it will be maximum. Okay, so this is a pattern. So the point is, as I said, what happens in practice is, it's not like for realistic data, real world data, it's not like a linear increase or linear decrease from some maximum value to 0 when m reaches n, but it's more like this kind of exponential decrease, where for m beyond a point, already error is quite low, so increasing m any further, right, does not really add value. So let us see how this whole thing works. Let us begin a very simple toy example. Let us say I have some data which is two-dimensional. This is x1 and x2. And data has a very simple structure. It's just a bunch of points like this. So you see that the points have a lot of variation in the x1 dimension, and x2 direction there is not much. So let us say this is say 10, maximum value is 10, this is minus 10. So these numbers are are such that in the x1 dimension numbers go from 10 to minus 10, but in the x2 dimension numbers only, let's say this maximum and min values is only 0.1. Okay, so I'm just taking a toy example. So there is a lot of variation in the x1 direction, very little variation in x2 direction. Now what we have done, what we planned to do before, is x is in Rn, y is in Rm, x hat is in Rn again. So let us say n equal to 2 because x is in R2. Then we need to decrease. So the only thing that you can do is at least take m equal to 1. So y is a scalar. Now x hat is again R2. Okay, so how do you pick this y? Right. So let us just common sense in this case. That if I just make y is equal to x1, right? Then so if I make y equal to x1, then if I only take all the x1 components and ignore x2 components, then this data set will become like this. All the points are strictly on the x1 axis, right, going from minus 10 to 10. On the x2 axis, all values are 0, set to 0. All right, so this is so anyway, we just have like y, only one y, which is equal to x1. Right now, how do you reconstruct x2? If you reconstruct x2, it will look like this, right? Y is equal to only x1. If you reconstruct x2, then x2 becomes 0. So we are left with this data set. The original data set had a variation in the x1 direction from minus 10 to 10. In the x2 direction, variation is from minus 0.1 to 1. Now in the new data set, right, the variation in the x1 direction is still the same, but in the x2 direction it is completely gone. But point is, so that means if we have a point here, let us say that point is, let me call this the point P, and let us say the point P is like no. Point P is some 5 comma 0.03. Okay, so I have a point like this because the variation in the x direction is not much, right? So I take a point like this. Now after the compression reconstruction, I get a new point called p hat, and the new point, the second dimension is ignored because of this reconstruction. So I have 5 comma 0.03, which is not bad. I mean, p, when you reconstruct, if you get this is pretty okay, right? Now, so this is a toy example. How do you do the same thing in a more general case? Let us take a slightly more general case where the data is not exactly laid out like that, where all the variation is in the x1 direction and nothing or very little in the other direction. Let us take a slightly more general case, but again in 2 dimensions. This is x1 direction, x2 direction, and now all the variation is in some other direction, not along x-axis, right? But again here also the variation is more in one direction and not much in the orthogonal direction. So the variation in this case happens to be in this direction. So in the perpendicular direction, there is not much variation. So now if you want to reduce, so again x is in R2, so therefore y is in R, x hat is in R2 again. So now you have to multiply x with some weight, because this is a weight matrix you have to multiply with. So now the weight matrix will be like a column matrix, right? So therefore y is a scalar, so I can just get y by multiplying x with a column matrix, right? So I want this y w to be this direction. So that if you multiply a given, so let me expand this part a little. So if I have a point here in the data set, which has a long component in this direction, but a short component in the orthogonal direction. When I multiply, so W is a unit vector because I'm only talking about direction and not interested in its magnitude. So it's unit vector. So I take a point here, right? There is a little variation in the orthogonal direction to W. This is W, and there's a lot of variation. So its component along W is big. So I take a dot product of this data point onto W, which is what I'm doing here, and I get the projection value, which is something like this. So that projection value is y. So this projection is y. So now, how do I get the new reconstructed data x hat? In x hat, right? This point will be the coordinates in x hat. So it will have like x1 hat and x2 hat. Okay, so x1 hat is so this point is in this direction of W from the origin. So you see that it's able to capture only the variation along the W direction, but not this. But that's okay because most of the variation is in the W direction. So now the question is, what is W? Right? What is W? Where if I project onto W and reconstruct, I'll neglect only very little. Okay, I'll capture most of the variation. That means I need to find W where, which is direction in which there is most variation. What does that mean? Variation here is simply given by this dot product of W and X. Okay, so what is then the question now becomes, what is W such that y square, right, average, so that is mean value of y square is maximized. So for example, you see that if you take this orthogonal direction where there's not much variation, right, your y square will be small because projections of the data points in this direction will be all small. So there's not much component in that direction. Projections of data in this direction will be highest. So I want to know, so this is projection. So I don't care whether the projection is on the positive side or the negative side. The projection on this direction, this side will be negative. I don't care about the sign. I want the magnitude to be highest. So therefore, I'm taking y square and taking average of that over the entire data set. I want this quantity to be maximized. So what is W such that E of y square is maximized? So how do you do that? So let us calculate this. Y is equal to W transpose X. So y square is equal to W transpose X times W transpose X. So this you can write as um, W, sorry, W transpose. So this can also be written as W transpose X into X transpose W because it's dot product, right? It's symmetric. So this becomes X transpose into W. So now mean value of, so that is average of y squared is equal to the expected value of y squared is equal to the expected value of W transpose XX transpose W. And W is a fixed matrix. There's nothing like expected value of, sorry, or fixed vector in this case. There's nothing like an expected value of W. But XX transpose is one data, is coming from one data point. X is a data point. So the expected value now, the expectation operator is applicable only to this part of the argument. So I'm taking out W transpose out. So this is what we get, right? So the average, so the expected value of y squared becomes W transpose times expected value of XX transpose times W. So what is the expected value of XX transpose? It is nothing but 1 over n times sigma XX transpose, where X is in the data set. So S is the data set. Okay, so you calculate this matrix, is a data matrix, right? And plug this in here. And so we'll call this matrix is actually called, popularly called autocorrelation matrix, but more precise terminology is covariance matrix. We'll just call it autocorrelation matrix. Because note that this is a matrix, and I'll define this, use the notation R, which is equal to X, average value of X transpose. So therefore, now your expected value of y square becomes W transpose RW. So now what do we need to do? Find W such that this quantity is maximized. And this is our familiar quadratic form, right? R is a constant matrix. Now this function is a quadratic function of W, right? With R, the elements of R playing the role of parameters or coefficients of the expression. Now thing is, so now R is actually, can somebody tell me what kind of matrix is it? So this is XX transpose, is outer product. So the elements of it are symmetric because ijth element will be xi xj and jth element will be xj xi. So therefore Rij is equal to Rji, symmetric, right? So this is one property. Second thing is, so you see that W transpose RW is actually average of y square. So this is how actually we started out with this expression and we got this. So you can see the right hand side is always at greater than or equal to 0. Actually, it's typically strictly positive because there will be at least one term where it is positive. So I'll just may call it, strictly greater than 0. So if W transpose RW is always greater than 0, what does it tell us about R? R is positive definite. These are the two properties of R. So from this, we learn that since R is symmetric, right? So R is symmetric. Therefore, values lambda I are real, and R is positive definite. So therefore, the eigenvalues are all positive. So these are very useful properties. We'll use them later. Now, how do you maximize this? Now, thing is, since it is positive definite, then it doesn't have a maximum, because if I take W to infinity in magnitude, it will keep on increasing. And we also know that we have also already said that we need W to be unit vector. So we put this condition. So therefore, we use some kind of a extended cost function where you want to minimize W transpose RW plus some lambda times. So mod W equal to 1 means mod W square is also equal to 1. Right, so this is your Lagrangian, extended Lagrangian cost function. So if you solve this, you get del E prime with respect to W. You set that equal to 0. You get 2RW plus. So actually, I'll take 1 minus mod W square here. I'll explain why that is makes it simpler. So you get minus 2 lambda W. So if you differentiate this, you get that, right, equal to 0. So therefore, RW is equal to lambda W. So this is the equation which governs W. Interestingly, you know that is nothing but your eigenvalue equation, right, for R. So which means that W is an eigenvector and lambda is an eigenvalue, right? So that is interesting. So now if you take a more general case, right? Just a second. So the weight vector is now seen to be an eigenvector. Now in general case, R is an n by n matrix. So there are n eigenvectors. And we also know that since R is a symmetric matrix, there exists an orthogonal matrix, right? Such that so orthogonal matrix Q transpose Q is equal to Q transpose is equal to I, and Q transpose RQ will be a diagonal matrix, right, which consists of all the eigenvalues. We have seen this result at long ago. It has all diagonal matrix as it has all the diagonal elements as eigenvalues. So now what we will do is we consider the more general case, that is input is X, which is n-dimensional. We project it first onto Y, which is m-dimensional, and then we'll reconstruct back to X hat, which is again n-dimensional. So if you do that, since the weight vectors are eigenvectors, right, and so let's say the first one is Q1, the other ones will be Q2, Q3, and so on and so forth. So I also assume that since the lambdas are all positive, I just assume by convention that so I let lambda 1 is greater than equal to lambda 2 is greater than equal to lambda n. So I assume that the lambdas are numbered so that they are all ordered. So now with this kind of arrangement, y1 becomes Q1 transpose times X, Y2 becomes Q2 transpose times X, and so on and so forth. And when you reconstruct X hat will be nothing but one to M Qi times Yi. Okay, so let's take the extreme case where consider the extreme case where n is equal to m. That is, there are as many you're not reducing dimension at all. You're taking all n dimensions. So then let us take, that means you'll have all the eigenvectors here, and the weight matrix then becomes it looks something like this, right? So Q1, Q2. So Q1, Q2 are all vectors. So I can use them as column vectors and construct a matrix. And this matrix happens to be an orthogonal matrix Q. Why is that? Because you can easily show that Q transpose Q is equal to Q transpose is equal to I. And why is that? Because Qi Qj is equal to 1 if I equal to j, right? Because these are all orthogonal, they form an orthogonal system, and assume they're all unit vectors, and is equal to 0 if I is not equal to j. Or more generally, you call Qi Qj is equal to this in Kronecker delta notation is equal to this. So this is called the Kronecker delta. Okay, so assume, so if you use all n dimensions, then y is equal to Q transpose x, and x hat then will be Qy. Then what happens if you substitute it here? X hat is equal to Q into Q transpose x is equal to x. So that means you have perfect reconstruction. So obviously this is a kind of, it is useless result because I want a reduction in dimension. I want to be able to express x using smaller number of dimensions, which is y. If I use all n dimensions, obviously I'll get a perfect reconstruction. Basically, we are verifying that intuitive expectation. So now, now we'll consider, instead of using all the n dimensions, if I use only a partial set of them, what happens? Okay, so x, let us consider now what we have just done above is x hat is equal to I goes from 1 to n Qi times yi, Qi times y. So this is what we have, which is and x is equal to, yeah, so the perfect x, right, is given by Qi yi, because if I use, sorry, x hat will be equal to m because I'm using fewer dimension. But I can get perfect reconstruction if you use all dimensions. So if you use all dimensions. Okay, so let me, sorry, made a mistake here. So x hat, I'm reconstructing using only m dimension. That is, I'm using only m terms here. For x, I can get a perfect reconstruction by using all, this is a perfect identity. So if I use all the n dimensions, I get a perfect reconstruction. So the error I am getting, E, which is x minus x hat, is nothing but sigma I equal to 1 to n Qi yi minus sigma I equal to 1 to m qi. So basically, this has all n terms, this has only m terms. So difference between these two expressions will be sigma I equal to m plus 1 to n qi yi. So this is the error. So instead of taking all the n components, if you take only m components, the error that you incur is given by this. So this is for one data point. Now, what is the squared error over all data points? Right. So let us consider that squared error over all data points is given as expected value of. So the squared error of this, it means this, right? Average over all data points. So this is nothing but E transpose E. Okay, so this is nothing but E times, sorry, E of sigma I equal to m plus 1 to n qi yi times sigma. Let me use a different index here, although it's the same expression. When I multiply, I have to distinguish a term coming from the first summation from the second summation. I'll use a different index j, m, q, j, y, j. So just consider this product, right? You'll get terms like qi, sorry, transpose qj. Okay, now, so we know that qi transpose qj is nothing but right from the previous page. Sorry, is Kroneker's delta. So that means if, so I'll have n minus m terms here and n minus m terms here. When I multiply them term by term and look at all possible products, only terms where you multiply the same term, that is ith term here and the ith term here, will survive. But if I and j are not equal to each other, such combinations don't survive. So therefore, this some product becomes E of sigma I goes from m plus 1 to n. If you only get qi transpose qi, so that is 1. So you get yi square. Okay. So this is what you get. Now we need to see what is this yi square, right? So we have seen that. Let us prove what it is. So expected value of yi square, right? What is this? So we know that yi is equal to qi transpose x. Expected value of y square will be qi transpose x whole square. Okay, and if you expand this like what you have done before, you get qi transpose e of xx transpose qi. So this is equal to qi transpose rqi, because this is r. You already defined this. Now this rqi we know is equal to lambda iqi from the previous equation where we derived this, right? So you get, therefore you get qi transpose lambda I qi, which is lambda I times qi transpose qi. Now qi transpose qi is equal to 1, so this is equal to lambda I. So the expected value of yi square is lambda I. So therefore in the previous case, in the previous page, we got that the squared error between the reconstruction and the original x which is equal to so this mod E square is equal to expected value of uh, sigma I equal to m plus 1 to n yi square. Okay, now the expected value of yi square is nothing but lambda I. So this becomes I equal to m plus 1 to n of lambda I. Okay, so this is a very important result. What is it saying? Let us try to unpack this. So we are going from x n-dimensional to y to x hat. So in the process, right, y is, so this is n-dimensional, m-dimensional, this is n-dimensional. So when I reduce this, I am getting an error which is given by sigma I goes from m plus 1 to n of lambda I. So let me, okay, just one sec. Okay, so let me explain what that means. So R has a bunch of eigenvalues. Okay, so R has a bunch of eigenvalues going from lambda 1 to lambda n, and they're all let's say strictly greater than 0. Now I'm plotting them, and we also have assumed by definition, okay, lambda 2 lambda n. Therefore, I'll plot them just as some kind of a bar chart, right? I is in x-axis. So I'm just plotting them there as individual numbers. So this is lambda 1, lambda 2. So these are the lambda values. So this is lambda 1, lambda 2, etc. This is, let's say some of these lambdas are very small as you go down. This is lambda n. So I pick m somewhere in the middle. Okay. So depending upon where I pick, so this is my m, let us say. Now, what is the error that I incur if my m is this? Right? The error is all the eigenvalues, right, beyond m, that is m plus 1 to n, the sum of all the eigenvalues, that is error. So if m is this, right, then the error is sum of all these values. So obviously, as I take bigger and bigger m, since the eigenvalues keep going down by definition, the error will keep going down, and if I take m equal to n, then there's no more eigenvalues left, so my error is 0. So what is the best case? What is the best way to choose m? Right? In fact, so what is the best? What are conditions under which I can choose a very good m? If lambdas decrease like this, like linearly, right? So there's only a linear decrease in error as you increase m, so which is not very profitable, right? But so if lambda variation is like this, okay, like a linear increase in m gives rise to a linear decrease in error. So it's not very profitable. But consider a situation where the variation in lambdas is like this. So there are a few eigenvalues which are very high, but after that it quickly drops. Right? Let us say I have 100 dimensions. Out of this 100 dimensions, only the first 10 have significant values, right? Let's say up to 1, 2, whatever. After everything drops to very low values, this is like a golden situation, really profitable situation. So in that case, then I can just take m to be some value like this. Then all the other eigenvalues add up to a small number, right? Now, now the question is real world data like this? The answer is yes. Okay, so in real world data, very often, uh, a small number, you have a small number of large lambda is and a large number of small lambda is. So therefore, it is possible to, so this gives us like a scope for strong dimensionality reduction, right? So this analysis is called principal component analysis. That is, you take the data set. So this is called principal component analysis. But a lot of people mistake this to, so this is not principal. Okay, because principal means important, key. These are key components, main components of the data. In which direction do you have the which components are the most important components? Right. So to finding out that is called principal component analysis. So for that you take the data, calculate the autocorrelation matrix, right, and then calculate eigenvalues and so, and if the eigenvalues, set of eigenvalues, the spectrum of the matrix, the set of all eigenvalues is of this kind, right? Then you know how to pick the top few eigenvalues. So that therefore pick m, right? And then so you get W matrix, which is Q1, Q2, Qm. Okay, so therefore Y will be W transpose X, right? And then uh, X hat will be WY. So that's how you can reconstruct. Okay, so now let us look at a numerical example of how it works. So data set is like this, right? The X component is 2.5, etc., etc. This is Y component. And when we study PCA, we first remove the mean value, right, from the data so that the data resulting data will become zero mean. Because if the data is like this, or distributed and far from the origin, right, then there's no point in looking at the direction of highest variation. There's only interest in direction. So you remove the mean value first, right? So change the coordinates like this, and then look at which direction it has highest variation. So you, for the given data, you calculate the mean, remove the mean from all the data points. Then the coordinates get shifted to the CG of the data. Right now the data looks like this. So the covariance matrix or autocorrelation matrix looks like this. And eigenvalues, we just take eigenvalues of this. Note that it's a symmetric matrix. And you can also make sure that check that it is a positive definite matrix, because you see that eigenvalues are positive. Now you see that the eigenvalues are actually very convenient because data has abnormal spread in one direction and very little variation in the opposite direction. You see that first eigenvalue is, okay, we need to reorder them. One of the eigenvalues is very high, 1.28. Second one is very low, 0.049. This is actually a great situation where you can get a lot of mileage. Even if you project all the data onto only this dimension, that is a dimension corresponding to this eigenvector, right? You can recover most of the data back with very little error. So in this case, the data is shown without the correction of subtraction of the mean value, but here it is corrected. Data has most variation only in this direction, and very little variation in the other direction. So find that and project it onto the first eigenvector, and then reconstruct back. Right? You get this in the reconstruction. You see that all the data points lie exactly on that line. In the original, they're almost on that line, but there's a little variation around that line. But in the reconstruction, you have thrown away the component perpendicular to this component. This you are neglecting. So therefore, in the reconstruction, you have all data points exactly on that line, which is okay, but because it's a reasonable approximation of the original data. And to capture this data, it is enough if I give one component. Actually, this data has two components, x1 and x2. But in the transformed coordinates of this and this, so this is y1, and if there is a y2, this will be y2. Right, in this transformed coordinates, it is enough if I mention y1 because y2 variation is very small. Right, so that's how you have opportunity for data dimension detection. Okay, so you can do some simple problems like this. Take a data set with a small number of points, and variation is mostly in one direction but not in the other. Follow these steps, and you can see how you can reconstruct the data. So with this, we are done with the topic, and actually we are done with the whole course. Because we have the exam coming up on this coming Saturday, right? And if you want any kind of revision or more any tutorial like an exposure on any other topics, let us know. Send mail to either me or Sandeep. We'll try to arrange something. But otherwise, the lectures are over.